This is CGTN, China Global Television Network.
I'm Somara near Oxford to witness an alternative method to generating power using nuclear fusion.
And I'm Emma Keeling, talking to a scientist who has a new hypothesis that may explain COVID-19's many different symptoms.
Nuclear fusion is considered to be the holy grail of clean energy. Previously on Razor, we visited ITER, the world's largest nuclear fusion experiment being built in the south of France. In a reaction chamber known as a tokamak, they will achieve fusion by creating and containing plasma in a magnetic field.
So here we come into the tokamak pit, and this is where you appreciate the scale of the tokamak. This entire space will be full from ground to ceiling with the tokamak. And the entire tokamak will sit inside this space, so you will never be able to come here. So here, exactly where we'll be standing, will be extremely cold, and then just a little bit up there. Yeah, almost absolute zero. And then as you just go up there in the middle, you imagine it'll be 100 million degrees.
But how will all this work to one day provide power? An atom of hydrogen is made up of one positively charged proton and one negative electron. It also has two variants or isotopes. Deuterium has one proton and one neutral neutron. Tritium has two neutrons. In a fusion reaction, deuterium and tritium fuse to form a helium atom and a high-speed neutron. In a fusion reactor, the high-speed neutrons will be slowed down by a denser metal wall surrounding the reaction. This slowing will release heat, which in turn will produce steam, which will then drive turbines. It may be possible to achieve nuclear fusion in other ways. First Light Fusion in Oxford are currently experimenting with what's called inertial confinement fusion.
So we're working on a new method for inertial fusion, which we call projectile fusion, where we fire a high-velocity projectile that hits into a fuel pellet, which we call the target, and that target focuses some of the energy of the projectile into hydrogen. Machine 3 is an electromagnetic launcher, so it uses electromagnetic forces to launch a projectile to extreme velocities.
Machine 3, or M3, is their latest prototype. They're currently running a series of tests, and they aim to fire a shot or pulse as often as possible to improve their methods. Just been told that there may not be a shot today. It's been a lot of stopping and starting, but the good thing is we get to go into the M3 enclosure to see exactly how it works.
Okay, after you.
Thank you. So this is M3?
This is M3, yeah. So M3 is a pulsed power generator. Now what that means is we store electrical energy up over a long period of time and we release that in a very short period of time. So we store the energy in capacitors. So these big blue things that you can see, they're high energy storage capacitors.
A capacitor is similar to a battery in that it stores electrical energy. The difference is that a capacitor can release a lot of energy very quickly, often in a second or less, unlike a battery which releases low amounts of energy over a long time.
We generate huge currents in the load, so up to 14 million amps we've seen on this experiment so far, and we put that current into our electromagnetic launch load.
To put that into perspective, 14 million amps is equivalent to about 500 lightning bolts. The average household power supply is only 100 amps.
There's no electrical hazard, everything is perfectly safe.
Okay.
It's just the trip hazards that we've got to deal with.
Wow, gosh, so the projectile and the target are in here?
That's right, yeah, this is where the experiment takes place. So right within the centre of this vacuum chamber, we've got the electromagnetic launch load. You can see there's 6 limbs arranged radially around the vacuum chamber, and the current flows down the limbs and into the vacuum chamber. There's a vacuum power feed through that we're just stood on top of. The current then converges within the vacuum chamber, and ultimately it converges down to a load which is this size. So this has 14 million amps flowing through it. That creates a huge magnetic pressure between these 2 conductors, and you can see that very shiny 5p piece of metal that shoots up this chimney, and that's the electromagnetic launch load. Now, so this is the electromagnetic launch side of the experiment, which is what M3 is used to do. The actual experiment then takes place on top of this electromagnetic launch load.
Because that's the projectile, isn't it?
This is a projectile, exactly, yeah.
There's still a target in there.
There's still a target, which I have here. So this target will be mounted on top of the load. The projectile strikes the bottom of the target, shocks propagate through the target, get focused and converge, and then they create the conditions inside that, the gas within this target, to create the conditions that we need for fusion.
And that's all happening in here.
Exactly.
The electric discharge creates a huge magnetic force, which fires the projectile at speeds of 20 to 30 kilometers per second. The target is a plastic cube containing a spherical cavity full of hydrogen isotopes, deuterium and tritium. The impact generates a shock wave that travels through the cube, collapsing the sphere, which compresses the hydrogen for a tiny fraction of a second. It's this sudden compression that generates a plasma, potentially triggering the conditions for fusion.
So we're eagerly awaiting to see the shot. What should we expect?
So we charge the trigger system, we then charge M3, it takes about 50 seconds. There's a lot of anticipation. All of the people responsible for the diagnostics will give the go-ahead to make sure that they're okay. We then, we go dark 10 seconds before the shot. So that means that we isolate all of the vacuum equipment, all of the pumps go off, all of the gauges on the chamber go off, and we make sure that that's all disconnected from the system before we fire. There's a 10-second countdown, and then we fire the shot. And it's an almighty boom. It really is quite impressive.
Some of the team are getting into hazmat suits. They're going to go into the M3 enclosure and try and figure out what the problem is. We've been waiting a long time for this shot, and today it hasn't been happening so far, so hopefully they'll get some answers.
Every shot that does take place needs careful analysis using a range of diagnostics and high-speed imaging techniques. Hugo Doyle is head of experimental physics.
So this diagnostic room serves 3 different areas. So this is one from one of our old shots, which we did actually on the gas gun, but it's a bit easier to interpret what's going on. So this is from this grey camera, and if I let it play, we get a nice film which is easy to interpret, and you can see our projectile coming in, and you can see it hitting our target. So as that target collapses, you get a shock moving through it in the gas, and that gas is getting hot and fast and beginning to glow. And then as it gets to the end, it's trapped in the rear of that cavity, and this is your preliminary kind of inertial confinement event, which is what we're looking for. We're trying to make this projectile go faster and ultimately hit our fuel harder, use a bigger hammer. And then the second thing we're trying to do, which is a lot of what the company's based around, is cleverer targets. And to put that in a different way, we're trying to more efficiently couple the energy from the projectile into the fuel. So if we can get that energy, more of the energy quicker into the fuel, we'll compress that plasma, that gas, and get it hotter and denser. And with the 2 of those methods, we can get it hot enough and dense enough for long enough to fuse and give off neutrons and get that fusion event. So that eventually, in the future, we're getting more energy out than we're putting in, and that's what fusion's all about.
Just looking at the screens that would have been fired up had there been a shot today, but I've just had news that they're not actually going to be able to fire one. There's been some issues with a pressure gauge, and it's preventing this shot being fired today. That's not to say it won't happen in the future, but Unfortunately, I've missed seeing it this time. That's science.
The research at First Light Fusion continues, and once they reach their goal of getting more energy out than they put in, they plan to supply power to the grid by a fusion pulse being created every 5 seconds. But this is still some way off, and for the next phase of experiments, they plan to build an even bigger machine. With ITER in France aiming to start their fusion experiments in 2025, and First Light Fusion making progress with inertial fusion, hopefully the dream of nuclear fusion power will soon be a reality.
Life moves pretty fast. Ideas move at the speed of sound. Technology moves at the speed of light. If you don't filter out the noise, you might miss the details. We pay attention to the details because they matter, showing you a different perspective. See the difference.
The world has changed under the pressure of the pandemic. For many of us, life is returning to some kind of normal. As we're adapting to changes in all of our lives, let Global Business Europe be your guide to the new normal. Join us weekdays on CGTN.
How will your world change today? What happens here? What happens there? Or what you make happen for yourself? If it matters to you, it matters to us too. Your stories are the stories that need to be told. Africa Live. Find your voice.
For patients suffering serious symptoms of COVID-19, it's as if the brakes have stopped working on their body's defence systems. But a team of scientists in America think they may have discovered why the brakes are failing.
We're excited about this model. The early clinical results are consistent with the model. That's really good news. We want to do further experiments in model systems to bear this out. We want to see clinical trials.
This is Dr. Daniel Jacobson, a computational systems biologist at Oak Ridge National Laboratory in Tennessee. With his team, he's been studying how the SARS-CoV-2 virus is doing harm. The Summit computer at Oak Ridge is the second fastest in the world, but it still took a week to analyse 17,000 gene expression datasets, which guided Dr. Jacobson and his team and helped them come up with what they call the bradykinin hypothesis. Bradykinin is a molecule or peptide made up of a short chain of amino acids that promotes inflammation. It's part of the kallikrein-kinin system, or KKS, and intersects with the renin-angiotensin system, or RAS, which controls many aspects of the circulatory system, including the body's levels of bradykinin, which helps regulate blood pressure and blood vessel permeability. Think of it as a system with an accelerator and a brake. The accelerator is depressed when you have an infection, and the brake starts to be depressed to keep the acceleration from getting out of control. The coronavirus affects the brake in the RAS and KKS. The virus effectively breaks the brake. Dr. Jacobson says a COVID-19 infection typically begins when the virus enters the body through what are known as ACE2 receptors on cells in the nose. It then travels through the body, entering other cells which have ACE2 receptors, such as in the heart, kidneys, intestines, muscles, brain, and lungs. When the virus hits the RAS system, the body overproduces and stops breaking down bradykinin.
We're calling this a bradykinin storm, where it's out of control, and that leads you to this spiral of outcomes. Excess bradykinin will lead to gaps in your blood vessels. It permeabilizes your blood vessels, so fluid will actually start to leak out. Your blood pressure will go down. You start to lose fluid. It also leads to inflammatory responses. And the immune cells in your bloodstream also now have a chance to exfiltrate, to squeeze out of your blood vessels into the surrounding tissues.
Dr. Jacobson's team believe the pathology of COVID-19 is likely the result of bradykinin storms rather than cytokine storms. Early in the pandemic, we heard a lot about coronavirus infections causing cytokine storms. Cytokines are small proteins released by cells in the immune system. They coordinate the body's response against infection and trigger inflammation. But sometimes excessive or uncontrolled levels of cytokines are released, which then activate more immune cells, resulting in hyperinflammation, a symptom common in those severely affected by COVID-19.
The cytokine storm hypothesis was a projection out of other disease conditions, other diseases where people have seen cytokine storms. And so we saw this sort of blitzkrieg of different symptoms that we couldn't explain in COVID-19, but there have been several papers by other groups recently looking hard for that cytokine storm and not really finding it. They're saying, sure, some cytokine involvement, but it doesn't seem to be going haywire. So that model is being challenged a bit by the scientific literature.
But a bradykinin storm ties together explanations of what's going on around the body. At these points of infection, Dr. Jacobson says they'd expect to see blood pressure going down and the leakage of fluid and inflammatory responses in the tissues.
We've mapped all those out, so we sort of know where to look. We said, well, what happens if we have a bradykinin storm in the intestines? Well, you'll get a lot of GI symptoms. You're going to get nausea, you're going to get diarrhea, you're going to get a lot of pain. Well, that's exactly what we see in a lot of COVID-19 patients. One of the bradykinin receptors is involved in pain responses. And we know from other conditions that excess of bradykinin will lead to very sore muscles and joints. And that's what we see in a lot of COVID-19 patients. What if this hits the brain? Well, you're going to get fluid leaking out of the blood vessels into the brain. And we've heard a lot about the neurological symptoms in COVID-19, the brain fog, the confusion, the headaches.
The world is still waiting for a vaccine, but with this hypothesis, if the research bears out, there are multiple therapeutics that already exist that can put the brakes back on this bradykinin storm. Are there any existing treatments that can be tested in clinical trials?
I think right now we're looking at about a dozen different drugs that can be applied here. We want to be very careful. We're always worried about the law of unintended consequences. There can be side effects of drugs, and you want to make sure you don't do something that accidentally makes something worse.
During their analysis, Dr. Jacobson's team made another important discovery. Using samples taken from inside the lungs, they compared a control group with COVID-19 patients. They found the virus also affects the hyaluronic acid in the lungs. It's naturally produced in the body, and its main function is a thin protective layer or lubricant.
When it hits water, it can absorb over 1,000 times its own weight in water. It becomes a hydrogel. And so what we saw in COVID-19 patients is the 3 genes that are responsible for synthesizing hyaluronic acid were all significantly upregulated. And 2 of the genes responsible for degrading hyaluronic acid, keeping it under control, were significantly downregulated. And you're also letting a lot of plasma, a lot of water effectively leak into that same space, and you're going to form a hydrogel. It's like having jello in your lungs. And those are the surfaces where you're trying to exchange oxygen and carbon dioxide. And that simply doesn't happen well through a hydrogel.
This could explain why some COVID-19 patients have suffocated even when on ventilator support. There have been past studies of hyaluronic acid getting out of control where X-rays showed spots throughout the lungs, which is common in severe COVID-19 patients. But a recent study also saw that in about half of the asymptomatic people with COVID-19.
Our fear is now with this latest paper, if this is already happening and people are asymptomatic, there may be a fair amount of damage going on that they're completely unaware of, but they can go from asymptomatic to a long hauler with long-term outcomes. And some of the long haulers are reporting that, is that they didn't have an acute infection, and now they're having a long-term consequence. So there's a spectrum in the long hauler communities between people who were hospitalized and severely ill versus those who had fairly mild cases or were pretty much unaware and then later started having symptoms. If all that is true, that really should change how we think about this disease, even from a public health perspective, because an asymptomatic infection, if that can lead to a long-term disability, that's a radical impact on society.
As America gets ready to elect its next president, CGTN is there, going beyond the race, focusing on the issues, the impact, and what it all means to America and the world. From international relations to fighting the pandemic to the global economy, CGTN brings context, perspective, and understanding. Watch coverage of the U.S. presidential election on air, online, and digitally across platforms. CGTN. See the difference.
Every story starts out like this.
Okay. We'll head up now.
But beyond the rush of the numbers, there's always a more fundamental question. What happened? Who has been affected? When market-moving decisions are made, who's responsible? And why?
Let's get some reaction on ground. Joining us in Johannesburg is Sutra Nairobi. Hello, Nairobi.
This is how all stories begin. See how they end. Only on Global Business.
Some of the most exciting advances in science come because of collaborations across different disciplines. In this case, the cooperation between a mechanical engineer and an Egyptologist opens up a new window into the past and also inspires a whole field of innovation through biomimicry. Professor Richard Johnston is based in the engineering department at Swansea University.
So how does engineering connect with ancient mummies?
So on our previous campus, the engineering building was actually right opposite our Egypt Center, which is an Egyptology museum, and kind of recently got a new X-ray microtomography machine, which we would use in engineering to look at things like jet engine parts or composite materials, typically human-made structures. But I knew someone who was in Egyptology and I'd been talking to them, and they passed me on to the Egypt Center. And when I saw the animal mummy samples that were down there, we just thought, actually, that's perfect for X-ray technologies.
The X-ray microtomography machine is similar to a medical CT scanner, but generating three-dimensional images 100 times greater in resolution. This allows the animal's remains to be analysed in extraordinary detail, right down to the smallest bones and teeth.
Historically, they'd actually physically unwrap mummified samples to see what's inside, and obviously that's incredibly destructive, whereas by non-destructively X-ray imaging, everything stays in that same position that it was thousands of years ago.
For the first time ever, the young scientists could peer into the undisturbed centres of some of the artefacts in the museum, time capsules into the past. A mummified cat yielded a surprising discovery.
It looks like an adult cat size, but actually the wrappings are really thick. And when you get down to it and you see that skull that's inside, it's a lot smaller. It was effectively a kitten. Virtual reality software meant that I could see different things within that data. So now I would literally put myself virtually within the mummified animal. I essentially make the mummified animal as big as my house, and I'm effectively touring through that, wandering through it, looking for a fracture or a break that we hadn't seen before when we'd been looking at 3D data on a 2D screen.
The researchers made a 3D printout of the snake skull to give to a biologist, who was then able to identify it as a juvenile Egyptian cobra.
Even if we'd unwrapped that mummified package, we would have ended up with a skull around this big, which is actually quite difficult to get the species from. So being able to then scale that up and 3D print it to something this large was really, really useful.
This immersive approach was able to throw a new light on ancient Egypt.
Some of the work we did, again, years after getting the data, it was really once delving deep into that 3D volumetric data inside virtual reality was really, really useful for trying to understand more about the animals and to give the right information to the experts that we were working with.
Did you ever think when you were examining jet engine components using the same technology that it would lead to this kind of investigation?
Not at all, actually. Through this project, it's shown the power of X-ray technology for me, and so I work far more outside of engineering now. We're scanning birds, insects, human tissue. We're looking at lots more than just those engineering materials now.
Professor Johnston now leads a team focusing on bio-inspiration, creating powerful images of tiny creatures. They're able to draw ideas from nature which can have a practical use in mechanical engineering.
We've been imaging a plant hopper, so it was discovered that they have mechanical gears between their legs. We're the first to kind of see them in 3 dimensions and try and understand their shape, because they don't look like human design gears at all. So we're trying to understand if evolution has led to a improved gear shape that could be useful for engineering.
Other species have inspired him too.
We have a campus that has its own beach, and so it was a curiosity thing. We have barnacles very nearby. We X-rayed them. And it was when we did that, I came to the microscope and saw an image of one tiny bit of the barnacle, the microstructure, and I hadn't seen anything that looked like that since I was working on jet engine materials with Rolls-Royce.
A jet engine has to be able to tolerate a great deal of stress from dramatic changes in temperature during use. A barnacle also survives in extreme conditions.
It lives in the intertidal zone, so it's half of its time spent in the water, half of its time spent out to the water, usually with waves crashing on it. And so the biomineralization or the underlying microstructure of barnacle could be tailored to different mechanical constraints linked to its environment. If there are challenging environments, then you need to do very interesting things with the materials that make up those structures. So yeah, it's strange how we see these parallels between nature and engineering. And typically nature got there first.